Thanks a lot also for the invitation. I don't see the chat, so please, if you have any question, just raise your voice, or maybe Flavio can tell me if there is any. I'm going to talk about Fortuna and uncertainty quantification in general. So Fortuna is a library that at AWS we released very recently in December last year, and we've been working ever since to really increase very fast the number of methods that we support, to try to support different use cases and so on. And I'm going to tell you a little bit about it, hopefully. So let's start. Let's start with really the most fundamental question: what is uncertainty quantification? And I'm going to frame the framework in a very generic sense. So you have an input that we are going to define as X. This input is fed into any model potentially. This could be a black box, it could be a neural network, it could be a partial differential equation, whatever you can imagine. And this model usually will spit out a prediction, a point prediction that we denote as y hat. Okay? So for example, if the model is trying to distinguish between dog and cats, it will say, okay, this is a dog, right? So this is my prediction. Now, you may imagine that in many applications, in particular critical applications, suppose you have a doctor that needs to rely on AI to decide whether they need to operate a patient or not, or whatever else. Well, it's very important not only to have a prediction, so do operate or do not, but have a measure of how sure the model is about that prediction. So in other words, we want to add information about the prediction that the model makes. So prediction, we don't only want a point value, we want to add a measure of uncertainty, okay? Whatever this measure is. Now let's make an example, okay? I've talked already about cat and dogs. Maybe the model has been trained on a classic data set of cat and dogs. And suppose that now it sees this sort of image, it's a dog that really wants to be a cat. So what should it predict? Well, the model is very confused, and maybe it tells you something like, oh, I think this image is a cat. Of course, the prediction is wrong, but we are adding information. You don't only have a prediction, you have also a measure of confidence, which is probability 55%, right? This is very close to the threshold 50%, so it's a very low confidence. And this is just really to stress that it's very important not to have only a point prediction, but also a measure of uncertainty. Now, unfortunately, machine learning models are often miscalibrated. But what does miscalibration mean? I'm going to try to explain it to you via an example rather than actually giving a formal definition. So let's explain calibration with an example, in particular in a context of classification. What is classification? It's just a machine learning framework where you try to classify a certain input. So you're going to say, okay, this is a cat, a dog, or whatever else. Basically, your target space is discrete. Okay. Now, indeed, consider a deep learning classifier, F. This could be any deep learning model, whatever. And what is very typical to do in classification is to say, okay, I'm going to say that F is basically the logits of the model. And I'm going to make predictions by argmaxing this output F. And at the same time, the probabilities associated to the prediction is going to be defined as something like a softmax of this logits F of X. Okay? So P is, if you want, a probability vector, because it's a vector and all the components are between 0 and 1, okay, and they sum up to 1. So you could interpret it to some degree as a probability vector. This is what people usually do. And yeah, and it's a probability for every possible class, right? So there is going to be a probability for cat, a probability for dog, and so on. Now, let's make an assumption, and this is what often happens in reality. Assume that all the probabilities of the predicted class for some test data xi, yi are very large. So you imagine you have a batch of data. You take among the probability vector, you take the maximum probability, so max of p hat. This max of p hat corresponds to the probability of the predicted class. And we assume, or at least we imagine, that this probability is very high, right? And this happens very often. You might find that the confidence that you obtain after you train a deep learning model is extremely high, something around 0.99% for every input, okay? Yeah, you might think that this is a little unrealistic. How come the model is so confident about every input it has seen and it hasn't seen as well? So intuitively, you might imagine that the probability that you have just estimated, this max of p, should correspond to some degree to the frequency that you classify correctly, right? So if I have n data points and I classify correctly m data points, then the ratio between m and n, so the ratio between m and n, so the actual accuracy, should match the maximum probability that you have estimated, so the probability of the predicted class. And now, a bit heuristically, if this happens, then you might say that the model is calibrated. If this doesn't happen, you might say that the model is not calibrated, okay? So I try to formalize slightly. This is not super rigorous, but this definition in this way. So you have an expectation over different data points of this probability of the predicted class, and this sort of should match the expectation over the data points of being correct, okay? Now, if this is approximately the case, you might say the model is calibrated. But unfortunately, in particular in deep learning, what happens is that this probability is much higher usually than the actual accuracy that you get. So as I said, you might get something like 99%, but the accuracy is much smaller. So we say that the model is miscalibrated, and in particular, it's overconfident. Okay, it's too confident about the prediction it's making. And now, this is a huge problem in practice, right? Let's go back to our example of the doctor that needs to decide whether to operate a patient or not, and it's based on AI. I mean, or you imagine ChatGPT, you ask ChatGPT, oh, give me the score about something, and it spits out something extremely overconfident. Then it's a problem if we are using uncertainty for a critical application. So the idea is that we want to calibrate these probabilities. We want to make sure to give something sensible out, okay? That's why maybe we come out with Fortuna. Fortuna is this library for uncertainty quantification that we released. It's open source. You can find it on GitHub. And let me tell you, what do we strive for? What are the principles that guide us? One is, of course, reliability. Everybody wants to be reliable. And what do we mean by this is that we try to include scalable methods across the full literature on uncertainty quantification. Let's say we don't discriminate. We try to be as inclusive as possible. That are good for estimation and calibration of uncertainty. A second principle is that the library should be intuitive and should really be, we try to bridge the gap between what's done in the literature so far, so experts do their algorithms, and just normal practitioners, normal data scientists, machine learning practitioners that might be non-expert in uncertainty quantification, but they want uncertainty about their predictions. So we want the library to be usable also for people that are not necessarily into the field. And we want it to be plug and play. Now, this is a very important property in a company, for example, like in AWS. If I go to my neighbor team and I tell them, hey, I have this great library about uncertainty quantification, why don't you just go and use it? Well, if I also ask them to retrain their models or to change the way they do machine learning, they're just not going to do it, right? So what we want is to complement rather what they do and add uncertainty quantification on top. And this is possible, maybe not always, but at least for several of the solutions that we provide. For example, conformal inference. This is possible. Okay. All right. So let's get a little bit more into the details, and let me tell you, at least for now, high level, what family of methods do we support? One is Bayesian inference. I mean, I put it here first also because this is Berlin Bayesian. So I'll give you a very quick intuition about Bayesian inference, but you might definitely not need it. The idea about Bayesian inference is that whatever you don't know is a random variable. So I don't know my model parameters overall usually, and therefore you might consider the model parameters theta as random variables. And as such, every random variable has a probability distribution associated to it, right? So in other words, even before seeing the data, I might say that my random variable, I have a prior belief, prior distribution about the model parameters. Now, if you merge the prior distribution and the likelihood function, so your understanding of the model, and you can think of this as a probabilistic version of a loss function in some way. If you merge these two, then Bayes' theorem gives you a posterior distribution, and therefore you can write a predictive distribution as I've done here. So the probability of observing a certain target variable given a certain input variable in the training data. And maybe the most fundamental, I don't know if it is, but the most characteristic question of Bayesian inference, we could say, is this marginalization of the predictive distribution with respect to the model parameters. And seen this way, in particular, when you try to approximate this integral with a Monte Carlo type of technique, so you average, you take some samples from the posterior and then you average them. Well, you might start to think that eventually what Bayesian inference is doing is some form of model averaging, right, in practice. And for that, you might also believe that instead of putting all your eggs in one basket, you're diversifying, and therefore you might argue that you are to some degree more robust. And so this is sort of Bayesian inference in a small nutshell. We will go back to it in a moment, but let me move to a second family of frameworks we try to support. Now, this is, I call it output calibration. You could call it parametric calibration. It's a very simple set of techniques that given a model, given the outputs of a model, so I just see the outputs, I try to attach an extra model on top, and then I calibrate only this extra part so that when I consider the full outputs, these are better calibrated and give me better probabilities. Okay. Now, the simplest concrete example of what I've been explaining is temperature scaling. So you remember I defined this before, this p hat, this probability for each class is a softmax of my model F. What we do here is augmenting my model F with the parameter tau, the temperature, and now defining the probability as softmax of F divided by tau. Okay. So if you increase the temperature, what happens? The probability distribution will melt down initially. So if you increase the temperature, then basically you're going to be less confident about one of your classes because you are melting down the probability distribution towards a uniform. And vice versa, you could also concentrate the probability distribution. Now, of course, this temperature scaling is a very naive or a very simple method, but in practice, it doesn't work that bad. It's very scalable because, of course, you're optimizing over a single parameter. You can definitely do better. You can, instead of tau, put another deep learning model, for example, input dependent and so on. And we support all of this in Fortuna, but this is a very simple baseline that I like to name. And finally, but not last, there is conformal prediction. This is a very exciting topic. In particular, in the recent days, it has been exploding. And for real good reason, I think, also because maybe one of the most important features of conformal prediction, I would say, is that it mostly acts, or it can act as a post hoc method. So you have already trained your model, you can even have already some uncertainty estimates, perhaps obtained with one of the other two frameworks that I've listed before. And you can calibrate this estimate to provide you a set of likely predictions with non-asymptotic coverage guarantees. Okay, so this set C of likely prediction. Now, if you are in regression, you could just think of an interval, literally like a confidence or credible interval, whatever you want. but this is like conformal interval. So if you want, is a calibrated version of what you might be doing with another framework. And if you're doing classification instead, this set is going to be a set of discrete likely variables, likely predictions. So if you're doing MNIST, where you have digits, it could be like a set of 149 for a certain input, and so on. But let me go forward. I will talk a little bit more about conformal prediction as well. Let me just check the time. Okay. So the formula I've written here, it's called marginal coverage. It's a probability over the joint distribution of both the X and Y. And what it's asking is that the probability that the target test variable belongs to the set is approximately 1 minus alpha. And it's the sort of guarantees that at least, well, the basic one, that conformal prediction tries to satisfy under the assumption, usually, this is the usual assumption, that the data is exchangeable. Now, if you don't know what exchangeable means, don't worry, just think of a slightly stronger version of it, which is IID, so independent and identically distributed data. If you assume this, then your conformal prediction method will guarantee you at least this marginal coverage. And you can also go behind this assumption of exchangeability and still have some good guarantees. Okay, so before going to the details, a little bit of details of these three familiar methods, let me say that for the way they are implemented in Fortuna, first of all, the whole library is in Python and is implemented in JAX. So JAX is like an analog if you want to PyTorch, not even. JAX is just NumPy plus auto differentiation. So you can just think of, I'm writing in NumPy, but I also get all the gradients and Hessian almost for free. And if you're doing Bayesian inference, since we do require gradients most times, we ask you to really write the deep learning models in a specific language, which is Flux, that is the most common deep learning library of JAX. But for the other two families of methods, they are postdoc so far, these calibration methods, and therefore you could have trained your model with any framework, whether it is PyTorch, TensorFlow, whatever. You just need to give me your outputs as NumPy. It's always possible, and then you can just use Fortuna. So we can say that maybe Fortuna for these two families is applicable to any framework. Okay, Bayesian inference in a nutshell. Maybe again, I probably don't need to explain, but let me go through it. Why not? So you have a model. This is at least the way that we think about it. So you have a model. This could be a deep learning model. It's usually a deterministic model. Okay, f of theta and x, where theta are the model parameters and x are the inputs. And then you have some other training data b. Now the model doesn't need to be necessarily pre-trained. Okay, so you don't necessarily need to give me a configuration of theta that has already been pre-trained. You can though, and if you do, I will use that configuration to start my Bayesian algorithm from a warm start. But I will still try to approximate a posterior distribution, and therefore I will still need to do some form of training, even if you give me a point estimate. Okay. Then, as I said before, theta usually are random variables, and therefore you define a prior distribution, and usually the most common choice for prior distribution, in particular in high dimensional setting, is a Gaussian distribution. And then Bayes' theorem gives you a posterior distribution. So the probability of the model parameters theta given the training data, x and y. And this you can rewrite as a likelihood function, so py given theta and x, times the prior divided by the marginalization of the numerator, which is also called the evidence, p of y given x. Now, just for information, this denominator, this evidence is something usually you don't want to deal with because it's difficult to approximate, and therefore most methods in Bayesian inference try to avoid using this denominator, like MCMC or variational inference. They all usually don't need to approximate this. All right, so you have now formulated a posterior distribution, but in most cases, the posterior distribution is not tractable. You cannot express it in closed form unless basically you have a linear model. And therefore, you need to approximate. Now there are tons of decades of methods doing this, and MCMC is a common example, variational inference, deep ensemble. You can think of SWAG, you can think of many different methods, and we support some of these in Fortuna as well. Okay, then I have approximated my posterior distribution. What do I do with it? Okay, I want to sample usually from my predictive distribution. So the way I do it is to first sample from my model parameters, and sorry, I sample my model parameters from my approximation of the posterior distribution, and then given the sample, I will instead sample my target variable y star. Okay, so I'm basically sampling from the joint here. And then after I have my samples y star, often what I want to do is estimate some predictive statistics. This could be predictive mean, predictive entropy, variance. It could be credible intervals. It could be whatever you want. Okay, and often this you might be able to formulate it as an expectation over some arbitrary function h of y star. And then it's typical to approximate this expectation via Monte Carlo using the samples that I gave you just in point 4. Okay, this is a Bayesian inference in a nutshell, at least the way I see it. All right, so let me move to the next framework. Again, this is output calibration, as we were saying before. And this is something very simple, I would say, but practical, so we include it. You start from a trained model, okay? So F now doesn't depend on theta, it's already been pre-trained. What you're gonna see is just the outputs of this model, okay? F of X. And you're gonna provide me also a validation data set. So you're gonna train your model, and then you keep a holdout data set aside, and you're gonna use this data set for validation or calibration in this case. Okay, so what we do, as I said before, starting from the model, from the output models f of x, we are going to concatenate another model. So this g of phi is an extra model that starts directly on the outputs of the model f of x. And this is a model that is parameterized by phi. Okay, so if you consider the g of f, this is basically the full model. And then I mean, we can. Oh, right. By the way, if you wanted to do temperature scaling, now g would be basically f divided by tau, where tau you could think of it as, or phi in this case, right? Okay. And now you do something very simple. I mean, you just try to define a loss function according to your task. I mean, it could be mean square error in regression, cross entropy loss, classification, and then you optimize with respect to the extra model parameters that you have just defined, so phi star. Very classic, nothing new. It's just that we are adding a model and we are trying to remove some of the overfitting given by the training data by comparing against another validation data set. This is sort of the point here. Okay, and then given this full concatenated model with the optimized phi, you obtain calibrated outputs, and therefore you obtain predictions. Simple way. Again, temperature scaling is a subcase of this. You could add, instead of the temperature scaling, you could add any deep learning model on top of your model. This is all supported by Fortuna, and yeah, you could calibrate your predictions. Conformal prediction. Okay, let's now talk about this. At least we're going to talk about split conformal prediction, to be precise, but we don't need to go into the details. And as I said before, you usually start from an already given uncertainty estimate. Now, if you're doing classification, this could be the class probability vector, it could be quantiles, both in regression and classification, standard deviation, some form of uncertainty. It could be an ensemble. It depends on the method, but you know, something. You give me something, and I do something after. Okay, then again, you will need a validation data set and some tolerance level alpha. So you could think 0.05 if you're trying to obtain some form of 95% interval or set, for example. Okay, so maybe the key crucial point of conformal prediction is that you try to define an agreement score function. Actually, I should have said maybe a non-agreement. This is a non-conformity score. It's usually defined as. So Sx of x, of S, x, and y, okay, is a non-conformity score. So it means that it tries to measure the disagreement between y and the model applied on x, okay? Now you could define your non-conformity score in the way you want. The idea is that the larger the score, the worse the agreement between x and y. A simple example, maybe the simplest in regression, is to define the score as an error. So you could take the absolute value y minus f of x, where f is your model. Okay. Now notice that f of x is already being trained. It's already your given model, right? And so you can do all of this a posteriori, eventually. And I'm not assuming, by the way, anything on the model parameters, any distribution on data. So that's also why people refer to conformal prediction as a distribution-free setting, because you don't make any distributional assumption, really. Okay, then you compute a quantile. Now, forget about this ceiling, n+1, minus, this is only to be precise, but for n large enough, you can see that that quantity there is basically just 1 minus alpha. So what you're doing here is just computing the 1 minus alpha quantile of the scores evaluated at your validation data. So to repeat, I take my score function, I evaluate it at each of my validation data points. So I will have, I will have a vector of scores, evaluations. And then I just take the 1 minus alpha quantile. Okay, so mp.quantile of this scores, like numpy quantile, and you get your quantile q hat. Okay, cool. And now what we do, you're given a test input, x of test, and the way you construct the prediction sets is the following. So you will include into your set all the possible predictions y, such that the score evaluated at x and this possible prediction y is less or equal than the quantile that you just computed before, so q hat. In other words, you're adding to your conformal set, to your prediction set, all the y that conform well with the quantile that you have computed before. Okay. Now, again, if you're doing regression, this set could just be basically an interval. If you're doing classification, let me give you an example. I mentioned this before already, but suppose now that this this input x test is a digit. I drew it myself. I tried to make it a little difficult so that you don't know necessarily what digit this is. And since you are uncertain about it, you would expect that your prediction set might contain multiple digits, right? So this could be a 1, it could be a 4, a 9, whatever. I completely made up this example, of course, but you know, just to give you an idea, this could be the form of the conformal set for this particular input x test. Okay, and again, this will give you some. You will have some coverage guarantees by using conformal prediction over this set, meaning that you are ensured that the set will cover, say, 95% of the probability mass for sure. Okay, with finite sample size. Okay, cool. Now, right. Even
before you move on, there's a question in the chat from Sharmita, and she's asking, like, you've presented conformal prediction and also the calibration, and she's asking, maybe you will also talk about it later, in what cases should we use one method or the other? So a little bit of the application context.
Right, yeah, that makes sense. I mean, this is a very good question. I think to some degree, also depends on your requirements. Suppose that you start from a non-trained model, or you start from scratch. Nothing, you need to use conformal prediction. Usually, you might want to anyway obtain an uncertainty estimate. So nothing forbids you to use Bayesian inference to obtain the uncertainty estimate, and then plug in conformal prediction on top and calibrate this uncertainty estimate. Right. So I think we shouldn't be, personally, I don't think we should be scared about combining multiple methods. And this is what we try to achieve in Fortuna. All of these three families of methods that I tried to describe, you can use them one on top of the other, but basically you could use Bayesian inference, you can do the calibration after, you can do conformal prediction on top. So it depends on your requirement. If you have already a pre-trained model, you won't allow me to see the model parameters. You have basically, this model is a large language model, so there is no way I can do any sort of training. Maybe it's just some fine tuning. You probably will struggle doing Bayesian inference unless you do some type of approximation, like Laplace approximation on the last layer of your, I mean, you can, of course, do, but for many people, it's just easier sometimes to use a post-hoc method like conformal prediction. So I think a lot of the value here is, there is some value in using these techniques. Then the output that you get is also slightly different. I mean, for regression, it's similar because in conformal prediction, you have an interval. In classification, you usually get a set in conformal prediction. So as I said before, a set of possible prediction. Now, according to your application, you might prefer to get a set, or you might prefer to get a number. Okay, so a probability. Maybe you want to threshold. It depends on the application. And I would tell you, try to evaluate for your use case what you actually want according to your requirements and what you want to obtain. And then even try to combine methods and see what works best. Yeah. I hope I replied. Please let me know if there is any other question. Okay.
I think that answers the question. Yeah.
Okay, cool. Yeah, one of the points I wanted to make actually is this combination features. I really think you can always try to plug one method on top of the other, and we shouldn't be scared about doing that. Conformal prediction eventually, or calibration, are methods that can work post-hoc, and why not? Why not to try to combine them, see if something works best? According to your own data, your own model, you will often find that some method will work better in one setting than the other. So yeah, let's go forward. Now, let me give you just a very quick idea of what the code looks like, how simple I hope it is, and how you can just get some uncertainty out there. So Bayesian inference, we start from there. What I do here is importing some objects from Fortuna. Then I create these posterior methods. So I have imported several of the methods just to give you an idea of which one. There is a map, okay, maxima posteriori, deep ensemble, automatic differentiation, variational inference. There is some form of Laplace approximation, SWAG. These are all possible. I listed a few, okay? And then I just wanted to show you here how easy it is to actually train a model, actually define a model, train it, and obtain predictive statistics as an output. This is a minimal example, of course. You can always configure, you can do much more, you can configure optimizer, select a prior, do all sorts of stuff, but I give you maybe the simplest version if you can just visualize it. So you have this for loop over the posterior methods. Now, you're doing classification in this little example. So what you define here is a probabilistic classifier. And as I said before, we try to complement, even in this case, we try to complement what the user usually does. So we assume that the user starts from a classic deep learning model, so an MLP, a multi-layer perceptron in this case. So what this probabilistic classifier does is a wrapper around this multi-layer perceptron that basically defines a prior distribution, a likelihood function, and eventually a posterior distribution under the hood, a predictive distribution, and you know. So with a very simple wrapper, you can basically obtain a probabilistic model. Again, you can do much more here. You can select your prior distribution and so on. And then you do prob model.train, and this train includes posterior inference, and calibration, parametric calibration if you give me data for it. So if you pass me some calibration data, then I will both try to combine the posterior inference that you selected and the calibration technique. Okay, and then finally, if you want to get some statistics, so now in this case I want the predictive mean, you could get the predictive variance, aleatoric variance, epistemic variance, whatever. You just need to do a probabilistic model, then call the predictive attribute and the mean attribute. Okay, and that's it. You will get some probabilities. Okay. So now, calibration, parametric calibration, output calibration. You can do something very similar here. Instead of a probabilistic classifier, you take a calibration classifier. So this object here. And this calibration classifier plays a role, like starts from the outputs of your model, okay? So you will take in inputs just the outputs, and it will do some calibration on top. Now, this by default does temperature scaling, but you could define any model on top. So you just call .calibrate, and then again, you could compute some statistics on top of it. Can you give me 5 minutes? I just need to run one moment to the toilet, to be honest, and then I'll be back if that's okay. Okay, then I will finish the talk.
Yeah, sure.
Just one question, Flavio, can you hear me?
Yes, I can hear you.
You seem knowledgeable. Can you maybe tell me a little bit about the non-conformity methods or measures for the conformal predictions? What would they look like in a classification setting?
So you mean that the methods that are not conformal?
This non-conformity score, was it called? I think. How you rank, how
I think
normal, so to say.
Yeah, the main idea is that usually they call it the scoring function.
Mm-hmm.
And the basic idea is that when you have some type of, I don't know, classification task, for example, you get the outputs of some sort of like pseudo classifier. Like, does the word softmax function say something to you or not?
Yeah. Yes.
So for example, the outputs of a softmax function, like they are pseudo probabilities. So they go actually from 0 to 1, and they add all up to 1, but they are not actual probabilities. So they're not well calibrated, which is kind of what Gianluca was saying. So the thing is that when using this scoring function, you kind of have this heuristic of how confident your model is about a certain prediction. So how well the data that you have fits with the class that you're predicting. And you can use this heuristic to do a more principled selection of the classes that you're more sure about. So this is basically what the conformal prediction thing is doing. I don't know if that kind of answers your question. Maybe Gianluca can add something to it.
Yeah, I think that makes sense. So basically, you use your softmax to get a set of possible classes afterwards, so to say.
Exactly. So this conformal prediction just gives you like this rule by which you can get a certain subclass of predictions with like certain guarantees. And I mean, it's not only reduced to like classification problems, but it's also like a more general topic that you can have whenever you have some sort of heuristic about uncertainty. So your softmax is in the end some sort of heuristic about your uncertainty. So that's
all right. Yeah, that makes sense. Thank you so much.
Someone posted something in the chat if you want to like read more on conformal prediction.
I think there is also an online newsletter by Christoph Molnar from LMU Munich. Mm-hmm. I didn't really check that, so I was like just heard about that. Thank you so much.
Okay, thanks Flavio for filling. Yeah, sorry about that. Yeah, I was talking quickly about this calibration model. This is another type of method that you can use instead of probabilistic model. You can define this calibration classifier, and this starts, as I was saying before, already from pre-trained model. So you just get the outputs of your model either evaluated on this calibration set, okay, and you can calibrate here. So and then you can get some predictive statistics again, like before. So it could be the probabilities, right? The confidence probabilities. And here in this calibration classifier where I have put nothing, basically here you define the model that will go on top of the outputs, the G model that I had defined before. And if there is nothing, if I don't include anything, then I will take directly temperature scaling. Otherwise, you can go fancy with your favorite model. Okay, so now I have a last code slide for conformal prediction. Here, you can call directly your method. In this case, we are calling a very classic method. It's called, well, we call it adaptive prediction conformal classifier. So you just call the method and then do conformal set. You will take the measure of uncertainty that you have in input. So in this case, is the probability. So it could really be the softmax evaluated on this validation set or the test set. And then you will take the vector of validation targets. So 0, 1, 2, 3, 4, you know, if you're doing MNIST, so on. And that's it. And this will spit out a conformal set for each one of your yeah, for each test target. Okay. Right. So this is a method, but we have many more. And actually, maybe let me show a little, if I still have some time. I hope you see still the screen. The list of methods that we have so far. So for Bayesian, we have this maximum posteriori. Now, I don't know if this is Bayesian or not. I mean, I don't care. You can consider this as a degenerate approximation of a posterior, basically a delta Dirac around your point estimate. We have a form of variational inference, scalable. We have some approximation of the Laplace approximation. And by approximation, I mean that you approximate the Hessian to be scalable again. So far, we have some generalized Gauss-Newton Hessian approximation. It would be nice to have more, but maybe it will come with time. Deep ensemble, I again list under Bayesian methods because I consider it just as a mixture of delta Diracs, if you want. You basically run your model multiple times. You will get several parametric, model parameters, and then you can just sample or get those to form your posterior. And SWAG is also a method that is pretty simple, works pretty well. It's basically doing stochastic optimization, so imagining a stochastic gradient descent, and using the checkpoints along the random trajectory to define a Gaussian approximation. So if you average the checkpoints over the trajectory, over the optimization trajectory, you will get the mean of the Gaussian, and then you can do some sort of low rank form of a covariance approximation as well. Then we have temperature scaling, but we don't have specific methods apart from temperature scaling. You could put whatever you want. Conformal prediction, we've been trying to really increase coverage here. We have some method for for classification. We have some methods for regression. We support some methods for time series forecasting and also for distributional shift. So this adaptive conformal inference is when the distribution shifts in time. MVP is for time series regression. We now can do also group conditional conformal prediction. So you obtain basically some guarantees for groups of inputs. So basically for population groups, you could think, ideally you could think, okay, for all the women against the men, or the men I'm sure that I'm not just having a guarantees over the full population, but really specifically on a set of inputs. Okay, this is what we have so far, but we are working hard to increase this. And by the way, if you are interested in contributing, just please let me know. It would be great to have more methods in the list. let me fly back to the list of supporting methods. And here is really just a final slide giving you the material. So we have a GitHub repository that you can access it. Oops, you can access it on GitHub. And by the way, maybe I have it even. Let me just do this. I will copy the link here. It's copied on the chat. And by the way, if you can put a star, you really help, because we are trying to grow fast. So if you can just put a star on the repository, really helps. And you can also access from there the documentation of the library, find the examples from the documentation. That's what people usually look at, but you can look at other things too. We launched a blog post at AWS when we released the library in December, and we also submitted now a paper on archive that you can also check by just typing Fortuna, blah, blah. Okay, so thanks a lot, and I'm happy to take some questions. I think we have 4 minutes.
I mean, there's no rush to, I mean, if you have to leave, let me know and we can.
I have time, yeah.
But yeah, there's no rush to finish. So before we get to the to that part, let me just stop the recording.